to follow. And so this very long title that I have here is a summary of the main takeaway that I would like you to have from the talk. And that is the idea that we use some sort of effective surface charge density to describe the driving force in electrochemical reactions. And this is not entirely new. It really is a reformulation of the Frumkin correction to the Butler-Volmer equation for the diffuse layer. And I will explain why that is, and the implications this has for how we should do our DFT simulations and for how we understand electrochemical CO2 reduction as well. And so first off, I want to thank the people who did all the work. And so shown in these pictures here are pictures of the first authors and co-first authors in our experimental theory calculations, both from Stanford as well as from DTU. And I highlighted the two members here who were fortunate enough to get talks at this conference, and these are the times when they are presenting. I also want to acknowledge all of the co-authors who contributed significantly, as well as the PIs who are driving the efforts. And so this here is the main takeaway, and it really is this very classical view of the potential distribution at the interface, where we have basically the metal potential and the distance away from the interface. And so when we apply an electrode potential, we can think of it as applying a potential difference between the metal potential and the bulk solution. Or we can think of it as relative to a reference electrode, but since the difference between the reference and the bulk solution is constant, then we can really think of the applied electrode potential in this way. However, what drives the reaction at the interface is not this bulk potential, but the local interfacial potential drop, as illustrated here, the drop between the metal potential and the reaction plane. And the critical part here is that this is not unique. One can imagine with a different ion concentration, that's the most usual way to imagine it, and that is Frumkin's idea, actually. But you can also set up the interface in different ways to make up a given applied potential. And so in that sense, then you would have a different driving force for your reaction. Okay. And this has implications for how we do our simulations, and it has implications for electrochemical CO2 reduction. And so my suggestion then is, instead of using this bulk potential, we should think in terms of this local potential drop. And this local potential drop, assuming that we have a linear drop within the reaction plane, is proportional to the field. And the field, through elementary electrostatics, is given by the surface charge density, because the surface charge density on a conductor gives the field right outside. And so this, I emphasize, would be a better descriptor of the driving force within the microscopic processes that are at play. And as I will mention later, it has implications for catalyst design. And so in this short talk, I will first talk about what this does to our electrochemical barrier simulations, which is very much an open field, and then talk about just a few insights into electrochemical CO2 reduction. Okay, so first starting with the barriers. Okay, so in contrast to reaction thermodynamics, for which we have the computational hydrogen electrode as a very well-accepted, established, widely used method, electrochemical barriers, the field is far from convergence. And I show in cartoons here just a couple approaches to that, the most common ones. And so if we are not dealing with proton-electron transfers, one can imagine that we can use the fully implicit or continuum approximation to the electrolyte. One can also think of working fully explicitly, which is more computationally demanding and comes with sampling issues. Or more and more, there is a drive towards hybrid approaches, which is a hybrid of explicit solvents with some implicit model of the electrolyte. And this offers us the advantage that one can, in principle, set a work function for your simulation simply by charging up your continuum electrolyte to some arbitrary charge. And what I want to emphasize in this talk here is that the Frumkin effect is also at play in these models of the interface, and it drastically affects the reaction energetics that we get out. And this effect is best illustrated with an example. And so let us start with a Vollmer reaction, which I have shown here as a cartoon. So it is a proton-electron transfer to the surface to form this simple adsorbed hydrogen. This is the simplest reaction that we can think of. And so dealing with explicit solvents, since we have no continuum charge, the only way we can vary the driving force is by altering the concentration of these proton-electron pairs. And what that really means in a simulation is that then we must change the size of our unit cell. And so this is quite a brute force approach, but it can be done, and Joe has done this here. And so we see here the Vollmer reaction energy as a function of the work function, and so we can get a certain relationship for the energy as a function of the potential. One can also imagine that we can perhaps apply some implicit charge like this, as I showed these schematically here, and that can also help us change the work function. Okay? And we can do this with a variety of different methods. There's many, many different proposed out there, but one is a linearized Poisson-Boltzmann model that's implemented in FAST. And so, however, when we do this, we get a multi-valued function depending on the cell size of our simulation. And so this is this implicit solvent overlaid with the explicit solvent results. And what this shows is that then in our simulations also, the work function does not uniquely determine the energetics when we have multiple charging components, because depending on the proportion of implicit or explicit charge, we have a very different local driving force. And what this also suggests is that existing results could differ, and on the order of 1 electron volt, if we were to simply take these models out of the box. And so what's the mitigation to this? And we go back to this picture. And indeed, this is a manifestation of the Frumkin effect, where the driving force is not uniquely determined by the potential. And so this is a fresh calculation just done by Siracek and Georg, showing that using a solvated Gilliam model developed in Andy Peterson's group, depending on whether we are charging the interface with an explicit charge, as shown in the solid lines, and the implicit charge, we get a very different potential drop at the reaction plane, and therefore explicitly illustrating this issue. And so what happens when we use surface charge? So if we were to take all the multi-valued functions that I showed on the previous slide and re-examine them as a function of this surface charge density, which I'm saying is a good descriptor of the local potential, then it all collapses onto a straight line. Suggesting that the surface charge density is a good descriptor of this driving force. And so my suggestion when we are doing barriers, and maybe this sounds a little left field, but it appears to work, is that we calculate our energetics as a function of surface charge density, and then translate that to potential, or to translate that to current densities using a microkinetic model, using known charging properties such as double layer capacitance and PZZ. And known is a very strong word because we do not generally know these quantities, but there's a back of the envelope kind of thing that we do in electrochemistry, and it's like when we don't know the capacitance, we use 20. And I would argue that because of the issue of this Frumkin effect, because of how large this effect is, this is still better than using just the work function. Of course, what I hope is that if you have done your simulations with work functions, the relative magnitudes of your barriers might be preserved, but there's actually no way we know that off the bat. And there's still a few issues with this, such as polar adsorbates also contributing to this effective charge, and what happens with a changing potential within our simulations and what that does to the chemistry. But this is the general idea that I'm suggesting. And so that's all I wanted to say about how we do our barrier calculations. And so now I'm going to move on to CO2 reduction. And I'm just going to pause for maybe 5 seconds here because I'm making a transition. Okay, and so the first topic I wanted to start with, and this topic kind of feeds into really almost all of our mechanistic understanding of electrochemical CO2 reduction, and this is the importance of field adsorbate interactions. And so what is quite unique about electrochemical CO2 reduction is that the intermediates that are important are very sensitive to the interfacial field, or really the surface charge density. And so shown here is a number of adsorption energies for some common reaction intermediates involved in electrochemical CO2 reduction. And what we find is that the intermediates with vertical CO bonds have really large dipoles. And so they vary significantly as a function of field. And so I show some examples here, CO2 and OCCO, and these, as I will discuss, are decisive for CO production and CO2 products. And this is very much related to the sensitivity of CO2 reduction to both pH as well as cations. And so as an example then, let us start with gold kinetics. Because gold reduces CO2 to CO, it is only a 2 electron transfer, so it's a really simple model system. But we can translate the insights that we get from that to CO2 product production as well on copper. And so let us start here with some experiments done by Carlos Morales group in Chris Hahn and Tom Hartneo's group. And shown here are the current densities as a function of voltage for both hydrogen and CO, shown on an SHE scale. So this is a sort of absolute potential scale. But what we can clearly see from these two plots is that hydrogen evolution, as we take it to acidic conditions, is very sensitive to pH, whereas CO production is not. And what this suggests is then that CO2 reduction to CO is not determined by a proton-electron transfer. And this is suggestive of a field-driven CO2 absorption being rate limiting. So my slide here is a little off, but this essentially is what we see from theory as well. And so we considered here some DFT-based kinetics coupled to mass transport, but actually the mass transport is not so important here when we're thinking about the reaction kinetics. And so this is the reaction mechanism that we considered, so CO2 absorption, proton-electron transfers, further proton-electron transfers. But what we find in our kinetic model, shown here, compared to a number of ECSA normalized current densities from experiments. And one thing I want to emphasize here is that the agreement here looks deceptively good. We never expect to get such good agreements when we're doing DFT because the errors in DFT leads to orders of magnitude. And so do not take this as an example that theory is so great. I mean, what we should be looking at is the general insights and the trends that we get. But the general insights here is that within the range of potential that we are interested in, it is CO2 absorption that is rate limiting. And so what this means though, and what I want to highlight here is that because this is the limiting step, then our Tafel slope depends on the dipole of CO2, as well as the double layer capacitance. And the field, which is proportionate to surface charge density, is determined by the double layer capacitance and the potential of zero charge. And so what this means is that when we are looking to design new catalysts, in addition to the reaction energetics, perhaps we can look at tuning the charging properties towards higher activity. And I hope to talk a little bit about that in the next 6 minutes. And another thing I want to point out here is that in general, what this model will tell us is that we do not need to look for 60 or 120 millivolts per decade. There's no reason to think of that. It can be anything in between because it's determined by the dipole and the double layer capacitance. And so in our reaction mechanistic analysis, we don't only need to look for 60 or 120. So before I get to how we tune these, though, I do want to mention one thing, and that is why high pH is advantageous for electrochemical CO2 reduction. And so I think for the kind of specialists in electrochemists, this is kind of like preaching to the choir, but it's also something that has caused a bit of controversy. So I just want to talk about it for just a little bit. And so the decisive steps towards CO and C2 product production are these ones. CO2 and OCCO formation. And these are sensitive to the interfacial electric field. The interfacial electric field is proportional to the absolute potential. So a potential, say, on an SHE scale. And this is the cartoon I draw here. And with more complex models, you still get a monotonic function. But this is the general idea. And And so what this means is that negative of the potential of zero charge of a metal solution interface, then we get increasing stabilization of these species. But the efficiency is determined on an RHE scale, and so for a given stabilization, what we basically get is a significantly higher potential at alkaline conditions than we get under neutral conditions. And so we can think of this dramatic pH effect that we see in CO2 reduction as the Nernstian shift to do with the reference potential. And in addition to that, nowhere here have we considered OH minus. And so you can produce a whole bunch of OH minus, but that is not helping your C2 product selectivity. It's the potential, because this is a potential-driven process. And this distinction is important. So now, in the next 4 minutes, I'll talk a little bit about how we can tune the double layer capacitance, and that is essentially the cadmium effect. And so our hypothesis here is that cations act in a very, very simple way, in a very classical view that I think is actually used quite a bit in biophysics. Cations have different sizes, they have different hydrated ion sizes, and that affects their packing density. And so I show here the case for lithium and cesium. And so lithium actually has a larger hydrated ion radius than cesium. It's got basically kind of 2 solvation shells. So we can pack a lot fewer of them at the interface. And really, the effect of this is again the Frumkin effect. So because we have a denser, we have denser number of cesium ions, we basically get a slightly larger field for a given potential. So there's a slightly higher driving force, and that basically reflects a slightly larger capacitance and a larger field. And so again, this is the Frumkin diffuse layer effect. Main takeaway: small hydrated radiums, high interfacial field, and slightly better activity. And this is something we can actually model in a simple continuum approach and then couple that with our DFT simulations. So it's basically separately doing a DFT simulation as long as surface charge density, and then coupling that to a modified Poisson-Boltzmann approach, which accounts for the volume exclusion due to the cation size. So this is a purely continuum approach. And what we see here in comparison to relative activities in experiments is, again, they do surprisingly well. And it compares well also to experimentally determined Stark shifts. But the main idea is small cations are good. And this is one way of tuning one of the charging properties of your interface towards higher activity. I just want to mention very, very briefly then, can we also tune the dipole moments? And the answer is yes. And this is what we have observed theoretically on single atom catalysts, where the localization of charge varies depending on the coordination of the central metal atom, and we find significantly different dipoles depending on the site motif, as illustrated here in the CO2 transition state energy as a function of surface charge density. And so when we translate to kinetics, this is what it looks like. And so these are theoretical curves for different sites, and so we can see that they have different tafel slopes. And what we see experimentally is that different groups report different tafel slopes. And so perhaps something like this at play, but what I want to emphasize here is this is not assigning a given site to a given catalyst, because of course we have not considered exhaustively the number of different site motifs that can be possible. And so then, just to summarize then, the main takeaways: use surface charge density as opposed to the work function as the driving force in modeling your electrochemical processes. And that's our adsorbate field interactions in electrochemical CO2 reduction give us new descriptors of CO2 reduction activity beyond simply the scaling and adsorption and transition state energies. And so these charging properties are double layer capacitance, PZZ, dipoles, and I will suggest that the cation size effect is actually tuning the double layer capacitance, and that we can furthermore tune the adsorbate dipole with single atom catalysts, which tend to localize charge a little differently from purely metallic catalysts. So In that case, then I want to end again with the people who did the work, and I'm so grateful to work with them. And that's